Hello everyone. Let's start. We continue with two examples from which they are remain from previous session. Any question from the previous session? Okay. Okay, we continue with this example for a SUF system with damper or damped SUF system. Here we have a railroad car of mass 2000 kilogram traveling at a velocity of 10 meters per second. Is stopped at the end of the tracks by a spring damper system as shown here. You can see. So we want to stop this car by using this spring and damper system. The mass of this car is 2000 kilograms. So we can assume that at the moment when the car achieves to the system, we'll stick to the spring and damper, and it will convert into a mass spring damper system as a SUF system. So we will have some initial condition. The initial condition for this problem is the initial velocity of the car, which is the initial velocity in fact of the mass, and it's equal to 10 meter per second. So x dot at t is equal to 0 is equal to 10 meter per second, and the displacement at t is equal to 0 is 0 because we assume that before the impact of the car and the system, a spring damper system, there is no displacement or deflection in the springs. So x at t is equal to 0 is 0, and x dot at t is equal to 0 is 10 meter per second. If the stiffness of the spring is K is equal to 40,000 or 40 kilonewton per meter, and the damping constant is 20,000 or 20 kilonewton second per meter, determine the response of the system. So we have CKM. Easily we can write the equation of motion for this system, and you only need to solve an ODE from order 2 with initial conditions that I mentioned. So we will have M, which is 2000, K is 40,000, and C is 20,000. Omega N is K divided by M, square root of K divided by M. You can form the equation of motion. For this problem, the equation of motion is 2000 x double dot plus C times by x dot, which is 20,000 times by x dot, plus 40,000 times by x is equal to 0, because in this problem there is no external force. Here we have one impact, which this impact is considered as an initial condition, so there is no external force. The natural frequency is the eigenvalue for the because here this is a damped system, the natural frequency is the coefficient of x in the standard form. If you divide the equation of motion by m, the coefficient of x double dot or the acceleration is 1. So the coefficient of x is equal to natural frequency squared. So we can calculate omega n, which is k divided by m. We can calculate the damping ratio. As you can see, this is the damping ratio. This term is the damping ratio, C divided by 2 times by a square root of K times by M. You can substitute K, M, and C and calculate. You can see that Psi or the damping ratio is more than 1. So this is the over damped system. The initial condition, as I mentioned, at t is equal to 0, x is equal to 0, and x dot is equal to 10. So we can substitute into the response, or you can solve the equation directly and use the initial condition to obtain C1 and C2, which C1 and C2 are constant coefficients for the homogeneous response. Okay, so you can substitute t is equal to 0. This is the response. You can substitute t is equal to 0 and obtain C1 and C2. Okay, any question from this example? Is it clear, or you need more explanation regarding the initial condition and how to calculate C1 and C2, or it's clear? Please let me know. If is it clear, we can move to the next example. If it's not clear, I can explain more, and I can explain how to substitute the initial condition and use the initial condition to solve this equation. Okay, we have another example I will explain, but about this one, is it clear how to solve this equation and how to form a characteristic equation and obtain the response? This is the homogeneous response, and how to obtain C1 and C2. Is it clear, or you need more explanation? I can explain in the software environment and explain there if you need it. Okay, so let me share the software and I will show you. Okay, can you see my desktop?
Yes, sir.
Okay, so we have an equation. The mass is equal to 2000. The stiffness of the spring is equal to 40,000, and the coefficient of the damper is 20,000. So this is the characteristic of our system. The equation of motion, if we call it EQ, is equal to the mass times by the second derivative of x with respect to time, plus c times by the first derivative of x with respect to time, and finally the stiffness K times by xt. Here, you know that in this equation, there is no external force. So the equation is a homogeneous equation. You can see this is m times by x double dot plus c times by x dot plus k times by x. This is the equation of motion. So we can form the characteristic equation for this problem. The characteristic equation is the coefficient of x double dot, which is m times by alpha squared, plus the coefficient of x dot, which is c times by alpha, plus the coefficient of x, which is k. So this is the characteristic equation. Now we can solve this equation, which is an algebraic equation. As I told you and I mentioned previously, you can solve this equation manually. I mean, easily you can use the delta method and solve this equation and obtain the roots for this equation. So here you can see we have two roots. As you can see, the roots are two real and distinct numbers. So because the system was an overdamped system, so the response or the homogeneous response is equal to C1 times by, if we call it the solution, C1 times by exponential of the solution first component multiplied by time plus C2 times by exponential solution second component times by t. So here you can see this is the homogeneous response, C1 times by exponential the first root, which is alpha 1. Alpha 1 in fact is the first component in this solution here. So the homogeneous response is equal to C1 exponential alpha 1t plus C2 exponential alpha 2t. Alpha 1 is minus 5 plus a square root of 5, and alpha 2 is minus 5 minus a square root of 5. So now we need to use the initial condition. We know the initial condition, as I told you, at t is equal to 0, x is equal to 0. And the second initial condition is at t is equal to 0, the velocity or x dot is equal to 10. So we need to these two initial condition. So we can substitute t is equal to 0 at the homogeneous response. If you substitute here t is equal to 0, you can see it will be C1 times by exponential 0, which is 1. If we calculate this or simplify this, this is C1 plus C2. So C1 plus C2 is the first initial condition with at t is equal to 0 here. When you substitute t is equal to 0 in your xh, so we will have C1 plus C2. So we call it the first equation, or E1. This is the first initial condition. The second initial condition, we need to calculate the derivative of xh with respect to time. Here, if you calculate the derivative of xh or the x dot, it will be C1 times by alpha 1 times by exponential alpha 1t plus C2 here times by alpha 2 times by exponential alpha 2. So this is the x dot. Now we need to substitute t is equal to 0. Subs t is equal to 0 in this percentage sign means the previous term. Okay, so here when I substitute t is equal to 0 in this sign, it means into the previous term. It means it will substitute t is equal to 0 in this term, which is x dot. Okay, so here you can see in this term it substitute t is equal to 0, so it will C1 alpha 1 exponential 0 plus C2 alpha 2 exponential 0. Okay, so this is the second equation. We need to simplify this term. Let me close. You can see this is C1. When you simplify this, we'll have this equation. But in the second initial condition, we have at t is equal to 0, it's equal to 10. So we will have this equation. When you simplify this, it must be equal to 10, or we can, when you move the 10 to the left hand side of the equation, it will be minus 10. So this is the second boundary condition. We have two boundary conditions. The first one is this term C1 plus C2 when t is equal to 0 at x. The second boundary condition is this term when t is equal to 0 at x dot, it must be equal to 10, or it will be minus 10, it must be equal to 0. So we can solve now. E1, which is the first one initial condition, and E2, which is the second initial condition for C1 and C2. So easily you can obtain C1 and C2. As I told you, you can directly solve again these two equations. I mean, from the first equation here, you can find that C1 is equal to minus C2, and then substitute here in the second equation. You can substitute, instead of C1 you can substitute minus C2. So we will have minus C2 times by square root of 5 minus C2 times by square root of 5 minus 5 C1 minus 5 C2. Again, instead of C1 we will substitute minus C2, so we will have plus C2 minus C2 will be cancel out each other, and finally you can obtain C2 from this equation, and then C1 is equal to the minus C1. As you can see here, C1 is positive square root of 5, but C2 is equal to minus square root of 5. So these are C1 and C2, and if you substitute this term, if we call it, for example, the solution of initial condition, this is, and then substitute the solution of initial condition into the homogeneous response, this is the final response for you. This is the homogeneous response, and we can call it, for example, XX, the response of the system. And if you plot this response, for example, for t is from 0 to 10 seconds, this is an overdamped response. Here you can see due to the initial condition, which is 10 meter per second, it start from, let me smaller this, make it smaller. Okay, here you can see it start from 0. Due to the initial condition, which is 10 meter per second, it will go to about 0.8, and then will again come back and will stop at x is equal to 0. So this is their total response, and after about 2 seconds you can see that the car will be completely stopped, or about here 3 seconds, at t is equal to 3 seconds the car will be completely stopped. So you can see here, by changing this value, for example, by changing this k or c, you can change this response. So if you as an engineer was responsible to design a spring and damper system for that car to stop this car and control the displacement of this car, you can change these values, the stiffness and the uh, damping constant, by changing this, because the weight or the mass of the car is constant, it's equal to 2000. You want to stop this car with this system, so you can change the k and c, and by changing k and c you can check your response, and you can see that how you can control the position. I mean, you can decrease this time by increasing, for example, c, you can decrease this time. After here you can see after 3 seconds the car will be stopped, but by increasing c, I guess this time will be decreased. For example, you can achieve to 1 second or less than 1 second, you can stop this car. So it's in your hand as an engineer. Okay, now is it clear how to solve this equation and how we use this uh, initial condition? Is it clear? Any question from this example? Okay, so okay, we can continue with the second example. Let me share. Okay. The second example, we have a boy riding a bicycle can be modeled as a spring mass damper system with an equivalent weight, stiffness, and damping constant of 800 Newton. So the weight is 800, the mass is 800 divided by G, which is 9.8. The stiffness is 50,000 Newton per meter or 50 kilonewton per meter. And the damping constant C is 1000 Newton second per meter, respectively. The differential setting of the concentrate block on the road caused the level surface to decrease suddenly, as indicated in figure. As you can see, this is the surface here at when x is equal to at this position 10 meter, we will have a decrement in the level of the surface by 5 centimeter. Let me show here. Here you can see this is the 5 centimeter decrement in the level of the surface. If the speed of the bicycle is 5 meters per second, determine the displacement of the boy in the vertical direction. Assume that the bicycle is free of vertical vibration before encountering the step change in the vertical displacement. So here, in this problem, you can see at t is equal to 0 because the origin point of time is in our hand. We can assume when this bicycle achieved at point A, this is t is equal to 0, or this is the origin point of our time. And after 3 seconds, because this length is 15 meter and the bicycle speed is 5 meter per second, so after 3 seconds, the bicycle will achieve, or system will achieve at point C. So at t is equal to 3 seconds, the bicycle will achieve to this point, B or C. And again, we will have another change in the level of the surface. So first, we need to obtain the response after t is equal to 0. And this is the response between t is equal to 0 and t is equal to 3 seconds. And again, after the t is equal to 3 seconds, we can solve another equation with some initial condition. The system is the same. I mean, the mass is constant. C, the damping coefficient or damping constant is a constant value. The stiffness is a constant value. So you can see the equation of motion is the same and there is no external force. If you extract the governing equation for this system, it's equal to MEQ times by x double dot. If, for example, we assume that this is the direction of x, the equation of this system is m equivalent x double dot plus c equivalent times by x dot plus k equivalent times by x, it's equal to 0. At point A, we will have some initial condition, and again at this point C, we will have a new initial condition. So first you need to solve the equation for point A. And at this point, at t is equal to 0, by assuming that there is no vertical motion before this change in the surface, so the initial velocity is 0. I mean, this mass before point A, it doesn't have any motion in x direction and it's completely at rest. So x dot at t is equal to 0 at point A is equal to 0, because here we assume that the bicycle is free of vertical vibration before encountering the step change in the vertical displacement. So at point A, there is no vertical motion. So x dot at t is equal to 0, which is our origin point, is 0. But x at this moment at point A is not 0. and it's equal to 5 centimeter. Okay, so we can, it's not 0, and we need some initial condition to solve this equation. So let's form the equation of motion and find the initial condition. Here you can see this is the x at t is equal to 0, which is 5 centimeter or 0.05 meter, and the initial velocity x dot is equal to 0, as I told you, due to the assumption of the problem. So we have one equation. This is the equation of motion with two initial conditions, this one and this one. Similar to the previous example, you need to obtain the roots of the characteristic equations, alpha 1 and alpha 2. You can form the characteristic equations, and then you can find the response, which is xt is equal to c1 exponential alpha 1t plus c2 exponential alpha 2t. So this is the xt, or the response of this system. Using the initial condition, you can obtain c1 and c2, similar to the previous example. So relate back to this here. So this is c1 and c2 that you can use to obtain, you can use the initial condition to obtain this c1 and c2. Now you have xt. The next step of this problem is to obtain the initial condition for this point c. Again, we can assume that we have a new origin of point, for example, t prime is equal to 0, but this time the initial condition will be according point c. I mean, here you can substitute in xt, you can substitute t is equal to 3 seconds and substitute here. So you will have some initial condition for t prime at t prime is equal to 0. If, for example, of course, we need to define a new x, it will, we call it x prime. It's equal to x at t is equal to 3 seconds. Okay, let me clean this. So for the next system of equation, we will have the same equation. This time, instead of x, we will have, for example, x prime. I define a new parameter, x prime. We will have the same equation, m times by x prime double dot plus c times by x prime dot plus k times by x prime. It's equal to 0. But this time, instead of these two initial condition, we will have two new initial condition. The first one is this: x prime at t prime is equal to 0 is equal to x at t is equal to 3. I mean, we use the response of previous part. We use the response of this time to obtain the initial condition for the time after t is equal to 3 seconds. And the second initial condition is x prime dot, or the derivative of x prime at t prime is equal to 0, or the velocity at t prime is equal to 0, in fact, is x dot at t is equal to 3 seconds. So you can see we will have again two initial conditions. This time you can solve the equation, and you know the solution, I mean, x prime is exactly as xt, but this time c1 and c2 will be obtained by using two different initial conditions, and we can extract two different c1 and c2. I mean, here we find c1 is equal to 0.05 and c2 is 0.012, but this time you will extract two different c1 and c2 for this system. Okay, I mean, after point C, the response has the general form like xt, but C1 and C2, or the initial condition and the constant coefficient in this xt will be different. Okay, any question? Is it clear? Okay, so the solution procedure is the same, and also you can use the formula as I mentioned in the previous slides. You can use the formula to obtain the response for an underdamped system. Here, this is the xt. You can obtain x, which is the amplitude, and phi, which is the angle phase, using these two formula. And you can easily write the response. The response will be the same, no different, but I always suggest the students to use the common procedure to solve the ODE and use the initial condition to obtain the constant coefficients, because it's not logic to memorize these formula. Of course, for this semester, maybe our exam will be online, and if it was online, you don't need to memorize any formula and you can easily use this formula, but you need to support your results by explanation. I mean, for example, if you are using this equation in your exam and you are using this formula and directly substitute x naught, omega, and v naught, and the damping ratio psi, you need to explain how you are using this formula, and you need to support your results by some explanation. Okay, any question? If it's clear, we can wrap up this one and start the new chapter and new part for this week. Any question? Okay, okay, we have less than 7 minutes, so we continue with an introduction of this chapter. In this week, we will start the logarithmic decrement and energy dissipated in viscous damping, torsional system with viscous damping, which is similar to the translational systems, and the graphical representation of roots and corresponding solutions. It's related to the control of the system. Here, you can see for an underdamped system, if you plot the response, we have something like this. As you can check, for example, the results of the lab test that I have uploaded, I already uploaded on Moodle. You can see we have some graphs like this, because as I mentioned in the explanation for the labs, even when we detach the damper in the lab, in the equipment, still we have some damping due to the friction and some other reasons. We have some damping, so you can see the same graph like this. And for a damped system, if you plot the results for a, in fact, under damped system, we will have exactly the same graph, maybe with different, for example, period or frequency, due to the different initial condition and different characteristic of the system. But the general form will be the same, as you can see here. And we will have some initial condition. For example, here you can see that this system start from some initial condition, some initial point here at this point. This is the initial condition with the amplitude x1 and phase phi. So this system start from this point, and the amplitude is decreasing by time. But if you measure for example, two consecutive amplitudes x1 and x2, and find the relation between these two amplitudes and write the equation, because you know, by solving the equation of motion you can obtain xt, and then you can find x at each moment. For example, at t is equal to t1 you can obtain x1, and at t is equal to t2, by substituting t is equal to t2 you can find x2. Then you can find the relation or the ratio of x1 to x2, and then substitute x1 according to xt. You can substitute x1 and x2, and for x1, as I told you, t is equal to t1, and for x2 t is equal to t2. But there is a relation between t1 and t2. As you can see, t1 and t2 are two corresponding for consecutive points. So t1 is t2 is equal to t1 plus the period. As you can see, t2 is equal to t1 plus tau d, which tau d is the period of the motion, and it's equal to 2 pi divided by omega d. And omega d is the damped frequency of your system, or the natural frequency of the damped system. If you simplify this equation and substitute for t2 in terms of t1 and the period, and simplify this, you can extract this equation. You will see that the ratio of x1 to x2 is equal to exponential of psi omega and tau d, which again tau d is equal to 2 pi divided by omega d, and omega d is a function of psi and omega n. I mean, finally, you can extract the ratio of x1 to x2 as a function of the natural frequency and the damping ratio. So you can simplify more this equation and find the logarithmic decrement by calculating the ln of the previous term. If you calculate the ln of two sides of the equation, I mean here, in this equation here, if you calculate the ln, we will have the ln of x1 to x2 is equal to ln of exponential of this term, which the ln of exponential is equal to the this term, which is the power of exponential. So the ln of x1 to x2 is equal to this term, psi omega n tau d. And as I told you, you can substitute for tau d, which is 2 pi divided by omega d, and omega d again is equal to the natural frequency omega n times by a square root of 1 minus psi squared. So you can simplify and extract this equation finally. So the logarithmic decrement, or delta, is equal to 2 pi psi divided by a square root of 1 minus psi squared. And if you convert or reverse this equation and find the psi or the damping ratio as a function of delta, you know, because this is an equation between delta and psi, you can write psi as a function of delta or delta as a function of psi. So here you can see we have psi is equal to delta divided by this term, and we can use this equation to obtain the damping ratio of the system. Our time is almost finished and we don't have time. We can continue on Wednesday, and because it will be suddenly will be interrupted, so I will stop this session, and thank you for your attention. So we can continue on Wednesday. Okay, thank you and have a good day.